Hello and welcome everyone. My name is Kelly here with Esri, and I would like to welcome and thank you for joining our webinar today. So today we're going to be discussing satellite-derived bathymetry in an integrated hydrospatial workflow in ArcGIS Pro and ArcGIS Bathymetry. And with that, I'll go ahead and turn it over to our first presenter today, Kyle Goodrich with T-Carta.
Good morning, and thank you for the introduction, Kelly. I'd like to extend my thanks to each of you for attending this webinar, and I'm humbled by the number of registrants and the Esri team for hosting and facilitating this event, and to Rafael Ponce in particular, who you'll hear from later on in the presentation, for being an outstanding business partner and a visionary in the hydrospatial industry. I'm going to jump right into our portion of today's webinar with a story map introducing our technologies, the hydrospatial community, satellite-derived bathymetry. Satellite-derived bathymetry is really a suite of technologies using a variety of radar, optical, video, and laser sensors in space to estimate, calculate, and model seafloor depths. Its origins date back to 1975 in Jacques Cousteau and the first Landsat satellite in calculating water depths in the Bahamas. In the 1980s, the US Navy used the GeoSat satellite to produce the first global deep-water bathymetric dataset. Today, there are constellations of sensors, technologies, and applications for satellite-derived bathymetry, and now we can achieve sub-meter resolution with sub-daily satellite revisits. Satellite-derived bathymetry is really a suite of technologies. There's 5 primary methods. I'm going to give you the basic capabilities, the limitations, and some of the key factors for each of them. First off, we have satellite or radar altimetry. This method uses radar waves to precisely measure ocean surface topography and compute the difference between the altitude and the ellipsoidal height to approximate geoidal heights and get water depths. Produced from this method, the eTopo 1 global bathymetry product is both an awe-inspiring product to view and also a very useful geospatial product for global and regional modeling, for seamount identification, geophysical, and geological studies. Second method is wave kinematic bathymetry. This method estimates the seafloor depths based on the repeated imaging of ocean waves and measuring their speed and spacing using radar, optical imaging satellites, or videos. It is by no means easy, but with consistent wave patterns, this can be observed from satellite from space. Bathymetric depths can be calculated from 0 to 35-meter depths and up to 70 meters, theoretically. This method has a unique capability in turbid coastal waters, as seen here in Guyana. Since this method is imaging waves and not seeing through them, water clarity does not matter. Stereophotogrammetric bathymetry uses traditional stereocartographic techniques to precisely calculate seafloor depths from high-resolution sub-meter optical satellite imagery. The most challenging element of this method is actually acquiring adequate and suitable imagery for this process. This process provides precise positional targets and depths of seafloor targets, obstacles, and submerged hazards in depths from 0 to 30 meters, but it's highly variable depending on the water conditions. It's used mostly as a secondary method and probably the least commercially exploited to date. Space-based laser not only is the newest method, but it's also just fun to say. Green 532 nanometer laser beams from space penetrate the water, reflect off the seafloor, and a lucky few return to the satellite and provide bathymetric depth measurements. This is way cooler than Star Wars lasers. The ICESat-2 sensor was not designed to survey the seafloor, but rather ice thickness, tree canopy, and elevation. But it's on a 7-year mission to describe the Earth in a sense, repeating over the same area every 90 days, as seen here in Pearl Harbor. What this technique does provide, it provides very precise coastal bathymetric depth profiles. It's an exciting technology, and there's a lot of focus on this technique right now in the satellite-derived bathymetry community. The last and most robust method, most widely known and recognized method of satellite-derived bathymetry is multispectral signal attenuation. This method uses multispectral imagery to model seafloor depths based on a variety of physics-based algorithms. There are a wide variety of satellites and constellations of satellites suitable for this technique and collecting imagery on a daily basis around the globe. Light penetrates water at differing depths depending on the wavelength of light. And shorter wavelengths in the blue-green spectrum penetrate deeper, while longer wavelengths in near-infrared and red very little, as evidenced in this illustration in the Bahamas. More of the seafloor can be seen towards the visible end of the spectrum. Since satellites capture imagery at these discrete bands of light, physics-based algorithms can calculate water depths. This method is the most commonly deployed and provides the most highest resolution satellite-derived bathymetry. It is utilized for coastal modeling, even nautical charting, with a variety of caveats, of course. Now, that's a summary of all the 5 methods. They all have advantages and disadvantages over traditional surveying techniques. all the methods are inherently remotely produced. So there's a cost savings, reduction of risk to people, equipment, and the environment, and an ease of repeatability that comes along with not needing to deploy any equipment to the investigation site. Of course, there are disadvantages, and no form of satellite drive bathymetry will ever wholly replace traditional hydrographic surveying methods like multi-beam or LiDAR surveying, as the precision and accuracy of the product will not match these other techniques. After all, it is a sensor in space, and ultimately the data is not for navigation, official navigation, and often used for navigational aid instead. Just to be sure, now back to my slides, and that leads us to our first polling question.
All right, thank you so much, Kyle. So what we want to find out today is, what is your level of exposure or experience with SDB, or satellite derived bathymetry? It looks like I have a majority in, so I'm going to go ahead and close this poll out and share the results with you all. So again, it looks like a good majority of you have heard of SDB but have never used it, and with 30% of you using SDB for a project at least once or twice. So again, thank you so much for your participation, and I'll go ahead and hand it back over to Kyle to continue the presentation.
Thank you very much. Great, and thanks for those replies. It's nice to see a good distribution. I'll try to adjust my information and balance it from here. Now that I've shown you a bit of the basics on satellite drive bathymetry, I'm going to shift gears a little bit and introduce you to TCARTA's Project Trident. This is a National Science Foundation Small Business Innovation Research Grant that TCARTA was awarded, and we're now in the early commercialization stages of this. Project Trident was designed to leverage these advantages that I've mentioned and address the disadvantages of satellite drive bathymetry by integrating numerous satellite drive bathymetry methods and deploying machine learning algorithms and remote sensing solutions towards large volumes of satellite imagery to produce a global bathymetry model. We've taken a multi-pronged approach here and offering a multi-pronged solution for our users. The results of the Project Trident are offered on a subscription data as a service, an on-demand data product, or as a do-it-yourself software as a service for particular users. Depending on your use case and what outcomes you're seeking in that satellite drive bathymetry, there's flexibility in our technology. So it's a matter of where do you want your satellite drive bathymetry expert in your loop. In order to address a lot of these shortcomings and disadvantages of satellite drive bathymetry, TCARTA has deployed deep learning models to address these specifically and achieve scalability. We've developed a deep learning technology to extract data at scale, and now our deep learning models are able to exceed our human operator in speed and accuracy. As you see here in our ISAT2 data, where we've extracted data from a deep learning model. We also offer Project Trident as a software as a solution, a software as a service solution, in remote and anti-access areas and for specific uses. An operator here can use software as a service to combine ISAT and multispectral satellite imagery to rapidly assess an area on the other side of the world from their desktop using Esri software. Within our data product offering, we are starting to combine multi-image composites, and this allows us to mitigate data gaps due to turbidity, clouds, and other environmental conditions within a single image. There's no shortage of satellite imagery available these days, so we can select the best of the imagery available within a time and create time series. Scalable satellite drive bathymetry production. This is really the crux of Project Trident, and here showing not only multi-images being processed, but here we've processed over 17,000 Sentinel satellite images and extracted over 500,000 depth points from the ISAT2 sensor and processed every suitable image in the Sentinel archive over the past 3 years, producing almost 45,000 square kilometers of 10-meter resolution data. Now, to put this in some perspective, because I know many people have heard of it but not necessarily used it, TCARTA has been producing satellite drive bathymetry for over 10 years. And just 2 years ago, this same project may have taken us over a year, and we would have used only 1% of these images. As the case is with this technology and how we deployed it with Project Trident, we started this project last Tuesday, and it's ready to go today. Additionally, we're continuously producing bathymetry data using these machine learning algorithms and these large data volumes. Here's another example, and I encourage you to take a deeper dive in our story map that's been shared to learn more about the technical details of our research in the background. And just as a quick overview of kind of what we've done and the concepts behind Project Trident, and it's a bit of a choose your own adventure of how you want to use satellite drive bathymetry in an organization, whether you want to use the global data service an on-demand data product for projects or software as a service and use it. And you can be your own expert within your satellite bathymetry loop. Whichever option is best for your organization or for your application, these technologies are built to be flexible and help make the most of satellite drive bathymetry. And that leads us to our second polling question.
All right, thank you, Kyle. So I'll go ahead and get the second poll question. You should be seeing that on your screen now. So if you want to go ahead and select one of the answers. And what we're asking today is, how do you foresee your organization using satellite-derived bathymetry? So it looks like, again, that majority stood. We have an on project-by-project basis with 55%, and then the 30% of you on a do-it-yourselves or in-house operation basis. So again, thank you for your participation, and I will go ahead and pass it back to you, Kyle.
Oh, thank you very much. Oh, that's an interesting mixture, and quite about what we see from our inquiries coming in. So it's interesting to see that. So whether you envision satellite drive bathymetry using the data product or becoming your own expert in the loop using our software, rapid data production and the recency of source imagery are key factors in using satellite drive bathymetry over traditional technologies. In both cases, satellite drive bathymetry provides an up-to-date view of the seafloor and often replaces data that is 100 years old, as is the case in this infamous incident this past summer, where the MV Wakashio ran aground in Mauritius and subsequently broke apart, spilled oil, and had to be scuttled offshore. Here on the right, we've rapidly produced and deployed to Esri technologies and Maxar SecureWatch platforms within hours of receiving a high-resolution satellite imagery. So instead of using data that's on the left that is 100 years old, you're able to use data that is just a couple of weeks old. And we get a short illustration of this event. As the Wakashio enters the Indian Ocean, it's immediately off course and then tries to make a course correction, but ends up heading directly towards the island of Mauritius. And as you can see here, as we're going to zoom in around the island, you're going to see the survey data from the nautical charts that because it's 2020, this ship ran aground right in between an 1897 survey and a 2010 survey, where there was absolutely no data on the nautical chart. Now, it's important to remember that the nautical chart had nothing to do with why this accident happened. The satellite bathymetry couldn't possibly have prevented this incident. But what it can do is provide the first responders and those trying to do mitigation work around the reef to provide actionable information of what's going on in the coastal area. As you can see here, we incorporated ISAT-2, and you can see the elevation profile on the reef of where the ship was run aground. We processed both 10-meter and 2-meter resolution. And if you notice, the 2-meter resolution satellite image was taken on the same day that the Wakashio entered the Indian Ocean, just by chance. But in comparison to using data that's from July 16th to produce bathymetry data for your recovery efforts around this island, or using a 100-year-old nautical chart with nothing on it, I think the choice is fairly clear. So that's just a brief introduction of how we produce data very rapidly in response to that accident in the Indian Ocean using our software and producing that data in-house. And then we were able to disseminate that information out to our community. And now I'm going to give you a little bit more of a background, dive a bit deeper into the software and how we produce this data within the ArcPro software environment. While TCAR's data product has advantages for analyzing and modeling, some people want rapid and hands-on production to support field operations. So we've developed several satellite drive bathymetry workflows within ArcPro that demonstrate these in 2 different places around the globe. First, we're going to go to the Canadian Arctic region in Alaktiak region. This translates to a good place for fishing in the native indigenous language in the Arctic. For TCAR, this translates into a good satellite drive bathymetry location. With deference to the indigenous people in the Canadian Hydrographic Service, we're showcasing this area in the Arctic hamlet. This is a bit of a satellite drive bathymetry test case for the Canadian Hydrographic Service, and they've published numerous papers here on satellite drive bathymetry and stereo photogrammetry. So TCAR has also kind of used this as a test bed to test our processes. So we've conducted our own trials here over the years, and satellite drive bathymetry works surprisingly well in the Arctic with clear waters. So there's a bit of a short collection season, and obviously this day is not so good for satellite drive bathymetry. But if you select imagery carefully and target task imagery and get suitable imagery, it works quite well. So to give you a brief introduction of what technologies we're going to use during this demonstration, we're going to use Sentinel imagery, worldview imagery, a random forest satellite derived bathymetry algorithm, and the ISAT2 data to train the algorithm. A brief introduction to the random forest algorithm. This is a machine learning satellite derived bathymetry process. It finds depth solutions from multiple multispectral band ratios, decision trees, trained with depths from the ISAT2 sensor in this case. It's only going to find depths where we've trained the algorithm to know that there's a depth solution there, so that it won't predict outside the depth range that we've trained. So here's a short video how we're going to use satellite derived bathymetry in Cambridge Bay in the Arctic here around this hamlet. We're going to bring in Sentinel-2 imagery at 10-meter resolution. We're going to use hydrographic survey data, and we're going to basically extend this hydrographic survey data, use the hydrographic survey data to inform our algorithm and be able to map the coastal areas and the surrounding areas. We can bring in ISAT2, and as you can see here, the ISAT2 tracks tend to capture data in the shallow waters, whereas this hydrographic data is in the deeper waters. So combining the two actually makes a very powerful training data set for this use case. So we've taken a sampling of this hydrographic data, about 1,000 points, and we've got about 1,000 points from the ISAT2 sensor. And if you look at a quick distribution of these points, you'll see that the ISAT2 points are heavily weighted towards the shallower depths, whereas the hydrographic survey data, because it's largely from a marine survey, are weighted towards the deeper depths. So combining the two, we get a nice distribution of training information for our algorithm. So we'll start showing the bands that are used in this algorithm, and then the workflow. We basically use the red, green, blue band, as well as the near infrared, and the operator can put in these parameters as well as the in situ data for training and any sort of title correction you want to put in. The process is made to be flexible, so you can bring whatever sort of in situ information you would want. And you can either run a very quick run or a full run, depending on what your application needs. So now you can see that the data comes out. You get a quick bathymetry surface of the whole area. We mask out the areas on land and some deep water areas. But you can see in this area here, there's some deep water area that needs to be removed. I don't think these bathymetric depths are true here. So we use the set pixel editor tool, and we're able to use the lasso tool to quickly select an area here where these depths, the depths that are measured here, are not actually measuring the bottom. It's just getting the extinction depth. So it's not actually receiving a signal from the seafloor. So we're just going to quickly set that data to no data, save our edits. And now we've got a quick bathymetric data set of the area. Now, I wouldn't say this data is anywhere near ready to go on a hydrographic chart by any stretch, but it's an initial data set you can start editing and interrogating and start making decisions based on. So now we can go in and look at an area here where we can compare the multi-beam hydrographic data to the satellite derived bathymetry data. We can combine, make the color ramps the same, so you can kind of visually see that the satellite derived bathymetry is picking up these same seafloor features. And then to another area here towards a very narrow passage as you enter the bay, where there's a navigational channel that's quite narrow. We're going to use 2-meter resolution data from worldview sensor to produce a higher resolution bathymetry model in this area. So here's our 2-meter resolution bathymetry data set with a 10-meter resolution data grid. And then we'll also bring in our hydrographic data. So now we've got 3 data sets over the same area along in this channel. And we're going to draw a quick elevation profile to see how well the data matches up using the path profiler chart. You'll see that as this profile pops up, the profiles match up quite well, except that the hydrographic data extends down below 14 meters to 17 meters or so. And that's largely our SDB doesn't get there because the algorithm was only trained to 14 meters. And it's unlikely satellite derived bathymetry is going to produce depths any deeper than that in this area anyway. So now we've kind of quickly produced quite a considerable area of bathymetry data in a relatively short period of time. And zooming back in on our hamlet here to see how good the fishing is in this area, we can now combine our hydrographic data and our satellite derived bathymetry to make a seamless, visually seamless bathymetric data set in the Arctic region. It's a tremendous reconnaissance tool for Arctic regions. As you can see, this is a huge area with lots of coastal waters. It's never going to replace LiDAR or multi-beam, but it provides a great reconnaissance tool for these remote areas which are challenging to get to and survey with traditional methods. So that was one example in an Arctic cold water location. Shifting gears to a warmer water location here in the Caribbean, in St. Thomas, U.S. Virgin Islands. Similar process here is our technology menu of what sensors and what algorithms we're going to use. Here we're going to use a Sentinel-2, and we're going to use the band ratio, the traditional method for satellite derived bathymetry, and we're going to use the LiDAR data. So with our software, you're able to bring in any sort of in situ information for use for calibration and training of our algorithms, as well as you need some of that data retained for validation so you can do quality assurance and know how good the data is at the end. Here in St. Thomas, we have a plethora of choices, and to use for in situ, we can use single beam, historical data, LiDAR, or even ISAT here. In this case, we're going to use the LiDAR data and this band ratio algorithm. This is a tried and true method. When it works, it works. There's no need to change physics, but it's not going to work in all situations. If you're familiar with the JEBCO Satellite Derived Bathymetry Cookbook, which is a widely used SDB method, this is a quite similar process, but with a lot of enhanced features and a far faster workflow. So I'm going to play a short video here of the data being produced by one of our SDB analysts.
Here we are in the Caribbean region. We'll be focusing on a location along the south side of the St. Thomas Island, U.S. Virgin Islands. A great place for satellite-derived bathymetry. We can directly access Sentinel satellite imagery from the ArcGIS Pro Living Atlas. Here we can search for the Sentinel-2 layer. Then you can select it and drag it into the map to view the layer. This layer automatically brings in the newest imagery, but this image may not be the one you want. This image in particular contains clouds and sunglint, which is not ideal as an input for satellite-derived bathymetry. In the raster item explorer found in the data tab of the image service layer, you can look through the archive of imagery to find an image best suited for the time period and location of your choosing. You can adjust the filter parameters for seasons, cloud cover, and date ranges. Once you have selected the image, you can simply add it into the map view. You can see this is not a perfect image either, as it has some cumulus clouds and boat traffic, but no situation is perfect. So this is a good example of a real-world scenario. Now that the source imagery is selected and ready to go, we can view in situ data for algorithm training. Here we have a NOAA bathymetry LiDAR survey and some single beam data, which are both great sources of training data for calibrating SDB. We can also use ISAT-2, a space-based laser satellite, which provides in situ equivalent measurements from 2018 to 2020. For this workflow example, we will use the Bathymetric LiDAR to calibrate the band ratio algorithm, and we will use a randomly generated subset for training and the remaining subset for validation of the final depth surface. This subsetting can be done in tCarta's in situ sample tool within the Trident toolbox, which allows you to subset randomly into two data sets at the percentage of your choosing. Now we are ready to produce SDB. I will adjust the image so that I can view the bands used for SDB, and we will begin to use the multispectral bathymetry tool within the Trident toolbox. The interface offers various options for processing, including masking out clouds, boats, and other discrepancies in the imagery. The mask uses NDWI, Normalized Difference Water Index, which deciphers between water and non-water pixels. The tool has other options, such as using a smoothing filter and the option to output a log so that you can keep track of the different iterations you run through the tool. The tool assumes the in situ is positive down, and it will output a matching positive down depth raster. The tool makes it easy to change these settings with just checking the boxes. After running the tool, the regression will pop up, giving you the opportunity to adjust the final fit to the in situ data, which will ultimately improve the accuracy of the depths calculated. Here we adjusted the data a bit and the fit is still not perfect, but the RMSE is very low, so the fit is close enough to continue with the SDB processing. After approving the fit of the model, the tool will take a few minutes to run on an average desktop processing machine. The bathymetry surface is output into the map window, and for viewing purposes, we are going to change the symbology to make it a bit more like bathymetric information. Now we can begin some visual interrogations to see how the process worked. As you can see, the masking removed the areas where the clouds were in the image from the depth surface output. Masking out boats is a bit more challenging, especially with 10-meter resolution, where the boats are often represented as a single pixel or two. You can see they were removed from the bathymetry data with the masking tool. If the mask was not successful, you can increase the masking value until these unwanted artifacts are removed. After visually inspecting the data, we can statistically analyze the accuracy of the results against the in situ data that was retained for validation. A quick review of the error shows a normal distribution with low mean error, so overall, the results statistically look quite good. We can investigate the points with higher error by selecting them in the bar graph, which then highlights them in the map view as well. For now, we can export these as another layer for further review. We can also review other statistics such as RMSE and absolute error, but a statistic we find helpful identifying small changes in shallow depths is absolute percent error. Opening the absolute percent error bar diagram, we can highlight the outliers of the absolute percent error and create another layer for review. Now let's zoom in to visually review these locations to see what the satellite-derived bathymetry looks like. The red points which had high error are concentrated here in the shallow areas with bright patches of sand among the seagrass. This could be an indication of changes in depths. In the south here, it looks like the masking parameter did not fully remove the boat wake. For small edits and data removal like this, ArcGIS's Pro Pixel Editor allows for easy cleanup of these outliers. After finalizing all edits, the bathymetric surface is ready for immediate use or ingestion into the bathymetric information systems using a bag creator tool.
All right, great, thanks, Caroline. So now you've seen a bit of how you can produce satellite-derived bathymetry on your desktop. And let's imagine now you have a license to produce that satellite-derived bathymetry. But just because you produce satellite data doesn't mean it's good data. So you have to fully understand the data and be able to manage and inform your subsequent users so that they can be properly informed to use the data properly. So good data can mean, this is a quote from a 25 leading experts, saying good data quality does not mean that the quality of the data is good or accurate. It means that the end user is well informed how good the quality of the data is. It's an important statement to being a data producer and a data manager. It's being able to discern good SDB data from bad and it'll catalog the data properly. Good data becomes useful once it's integrated through interoperability and adherence to data standards, and including uncertainty for the bathymetric data and the metadata that goes along with it. The Trident software includes export to bag bathymetric attributed grids for import into your bathymetric information system, along with metadata for proper data management and derivative product generation within the Esri environment. Now your satellite-derived bathymetry becomes hydrospatial information and ready to use. So this now brings us to a handover from TCARTA section to Raphael and Esri for theirs. But first brings us to our last polling question.
Okay, thank you so much, Kyle. That was a great presentation. So before we transition over here to Raphael from Esri, we have a polling question for you. What is SDB's most significant value proposition for you or your organization? And I see a good majority of answers are coming in. And it looks like, again, a good majority of you have voted. So I'm going to go ahead and close this poll out and share the results. And again, it looks like everything was split down the middle with coverage and anti-access areas being, edging out slightly over the others. So again, we thank you for your participation. And I'll go ahead and pass it back over to Kyle.
Great, thank you, Kelly.
Yep.
I'm ready to pass on to Raphael. Thank you very much.
Perfect.
And please feel free to add in the questions for the Q&A section.
Okay, thank you very much, and sorry for the momentary inconvenience with the technology. So we'll continue on this workflow from Kyle, and first of all, I want to thank Kyle for the very nice introduction of myself. So let's move to the next one. So first, I would like to, for those that are not familiar with the ArcGIS platform, to introduce the main maritime components of the system. In this slide, we have three main components. One is called ArcGIS Bathymetry, and the other one is ArcGIS Maritime at the bottom of the screen. And we consider those two solutions systems of record, which means you will use these two solutions to build your databases. The bathymetry one is a bathymetric database, and the maritime one is a nautical database for chart production. And when I say chart production, it doesn't constrain to the traditional or official nautical charts or specific ENCs or paper or raster charts. You can also create any type of custom chart from it. And on the top side of the slide, we have server. And with server, we have the maritime server extension that we consider a system of engagement, meaning that you would enable data and information products to be consumed by different users for different purposes in different types of devices. So with that, I would like to take from Kyle's excellent presentation and explanation of the process of acquiring and analyzing satellite-derived bathymetry. And once this data has been validated and is QC'd and QA'd, the data comes into the ArcGIS environment. In this case is the ArcGIS Bathymetry solution in ArcGIS Desktop. In this solution, we create a database that we call the Bathymetric Information System, or BIS, where we can store and analyze raster data and vector data, point data sets. So once we have our data in the BIS, we can combine these different types of data sets and make analysis, surface analysis. And we can also create bathymetric surfaces based on different criteria and use them for different purposes. One of them, and this is what we are going to see in this presentation, is a pre and post analysis of a hurricane event. Another possibility is to support hydrographic surveys for chart production. And as Kyle mentioned, this is something that you can use for exploratory purposes to evaluate the rate of change in a specific area and use it as a tool to estimate when you need to update navigational chart product. So with that, we go to production. And then in the demonstration that we will see today, we will see how to extract contours or lines of same depth to be used to create or to complement a chart product. In this case, we are estimating that this could be used for updating a small scale type of chart, for example, a general or an overview chart, maybe a coastal chart if the water clarity is good enough and the uncertainty is good enough for that type of product, but it'll be in combination with other sources. Nevertheless, I think after a meteorological event like a hurricane, having a quick, rapid assessment right after it happens with SDB is very useful for hydrographic purposes too. And finally, with this data, create an ENC and publish that ENC in the ArcGIS Maritime server for consumption. At the same time, the same data sets can be used to create a bathymetric elevation service. And this elevation service can also be provided to different users and combined with different services to do more analysis, to create more information products, and make decisions. So with this, I have the first poll of this section of the presentation. So Kelly, if you can bring it, yeah, here it is.
Sure thing. So everyone again should be seeing that poll question on your screen. So we appreciate your participation. So this question, how do you manage bathymetric data in your organization? And it looks like, again, that GIS system, that last answer there, held the majority with the files and a file management system coming in second, and then an essential database as third. So I'll go ahead and pass it back over to you, Rafael.
Thank you, Kelly. So we can see that the majority of audience are already using bathymetry in a GIS environment, which is great. The BIS, the Bathymetric Information System, allows you not only to work with bathymetry in a GIS, but also to organize the bathymetric data in a database. And here in this slide, I'm just explaining in a very general way how this ArcGIS bathymetry solution works. So we first, starting from the left side, we register data sets into the database, and what the database does is to register the location of those files. Those files can reside locally in a machine or in a cloud or different servers across the organization, even in different geographical locations. And it manages all of them and bring them together once we are exploring the data to build bathymetric surfaces or compose bathymetric surfaces. We can combine multi-beam, single-beam, LiDAR, satellite-derived bathymetry, and use that information for analysis and also for the creation of information products. So that's the workflow from left to right in general in the BIS, in the Bathymetric Information System. And now I will go directly into use case. So we first, we are going to see the how to add bathymetry into the BIS. And we have seen from Kyle's presentation in St. Thomas how they analyze some bathymetric data sets from SDB and create a bag and exporting a bathymetric attributed grid. So we are going to use that bathymetric attributed grid and register it into the BIS. But before we do that, I would like to go ahead with the second poll of the day in this section of the presentation. So please go ahead, Kelly.
All right, thank you. And this should be the last one for our presentations today. So if you want to get those answers in, how do you use bathymetric data in your organization? And I'm gonna go ahead and close this out. Thank you again for your participation. We appreciate that. That brings us a lot of good information. And it looks like the first three were pretty split in terms of answers, and with ports, operations, and maintenance coming in last. So again, thank you so much. And I will pass it back over to you, Rafael.
All right, thank you, Kelly. Yeah, very interesting. I think between producing nautical charts and oceanographic activities, we have like a tie almost. So it's a good balance. I think as we can see in these results, the use of bathymetric data is spread across the board in different disciplines. So let's continue and now move on into adding, registering bathymetric data into the BIS. So here we are going to add a data set, and you can see here, this is the St. Thomas SDB data that we receive from T-Carta in the bag format. As we can see here, there is some metadata that comes with the bag. That's why it makes it a very important type of format. You have one of the most important ones is the uncertainty value. And in the extended metadata, we can add some values like, for example, the data type, in this case, SDB, the platform, because it's satellite, we just put other. And we can also edit this extended metadata field and put more or less information as it fits our organization. So when adding bathymetric data into the BIS, what the system is doing is registering the location of that data set. It's not physically importing into my machine or into a specific hard drive that information. So now we open the Explore Bathymetry window, and we can see here the recently added bag file. And on the left side here of the screen, you can see a series of filters that you can use based on the metadata of those data sets. For example, we can filter the data by data type and just have the SDB data. In this case, we have two data sets. And we can create a bathymetric surface with those two data sets coming from satellite-derived bathymetry. So when we compose a bathymetric surface, in those overlapping areas, we could set some rules to make precedence for the data sets that we consider better. In this case, we are just adding one rule, and that's the cell size. And we want the smallest cell size on top because we have a data set that is 2-meter resolution. We are going to use that one as the precedence and create a combined bathymetric surface. So we can see here on the screen that surface we just created, and we can export that surface of those two data sets as a seamless surface. We give it a name. In this case, we are going to call it STB surface. And we are selecting a TIFF file as the raster format and apply some compression to it, and just click Save. So this is a GeoTIFF. So once it's exported, we are going to display that on the screen. Yeah, we want to display the layer on the map. And here it is. This is the new created layer from the Compose Surface window. Now, what we are going to do here is to change the color ramp. So we go to the properties, the raster functions here, and we select a color palette that is more familiar for us working with bathymetric data, where shallow waters are on the reds and oranges and yellows, and deep waters are on the blues and dark blues. And now we can see that here, and we have the SDB surface TIFF register, made and exported and ready to be used for many different purposes. We can share it, we can combine it with other data sets, we can extract bathymetry from it, we can create contours, we can do many different things with it. So now, before I show the next demonstration with the BIS and how we manage bathymetry in the system, I would like to just, for those that are not familiar with that technology, to clarify a few terms. So first is the BDI, what we call the Bathymetric Data Index. And we can think of it as a catalog of all bathymetric data in the database that are managed by a mosaic dataset technology within the BIS, within the geodatabase in the BIS. This mosaic dataset references bathymetry raster data, and it's and all these it's supporting tables, including all the internal metadata, the extended metadata, and also we can create metadata for collections of bathymetric datasets. So that's the BDI. Then we use the BIS catalog to explore and manage bathymetry. In this case, in the demonstration, we are going to explore point datasets using the BIS catalog. And I also want to mention here the mosaic dataset technology. This technology allows you to store, manage, to view and query from small to vast collections of rasters and image data. It is a data model within the geodatabase that is used to manage a collection of different types of rasters or images that are stored as a catalog and viewed as a mosaiced image. We can create pyramids where you can see the data at different resolutions based on the zoom that you apply to it, and we can also create overviews, as you can see on the picture at the bottom of the slide, where we can have overviews where you generalize the entire area with all the different components of the mosaic. Okay, so having said that, let's see how we manage bathymetry in the BIS. So here we are, and you can see here on the right side, we have this geodatabase that we created for this particular demonstration. And we bring the bathymetric data index into the screen, and you can see all the different footprints of the data sets that compose this BIS. As we did previously, we can change the colors. In this case, we're going to add again a bathymetric color palette. We can call it like that. We have, in this case, a positive up, and we can also apply different characteristics to the layer properties. We know the depths at which this data is, and we apply the range of depths to the color ramp, so it'll show up like we are used to see bathymetric data. And we can manipulate the presentation of it. For example, we can apply some transparency here, a 15% transparency, just to see what's below and have a better view of our bathymetric assets. So that's how you manage some of the BDI information there. So let's bring the catalog, the BIS catalog for vector data, for point data sets. And what you see here are the footprints of all those point data sets. And on the bottom of the screen, you can see the tables where you can check the attributes of all those data sets and where they are located. If we highlight one on the table, we can see also being highlighted on the screen to the corresponding data set. We can query this information on the screen and get additional information for those data sets. And we can see here at the bottom of the screen more information about that particular data set. So in that way, you can check what type of information you have available, what's the origin of that data, if it's raster, if it's vector data, if it's multi-beam, if the data is SDB, LiDAR, etc., and make your decisions to combine and create your bathymetric surfaces for further analysis and production. So that so far we have seen how to register a bathymetric data set into the BIS, and then a brief overview of managing bathymetric data assets in the system. Now we are going to see an example of a real world example of bathymetric data analysis after the Hurricane Maria that hit, I think, was in 2017 in the Caribbean. So we start here with our bathymetric data sets, and we are going to analyze this particular region in St. Thomas. As we have seen before, we have some new SDB data, and we are going to check and compare with existing data. So we know we have some LiDAR data, and this LiDAR data, and this is just for demonstration purposes, but this LiDAR data, which is very good resolution, is from 2011. And we're going to use that to compare the bathymetric surface in the region with post-hurricane SDB. So we can see here the data sets, and we select the area that we want to analyze. It's highlighted on the screen. This is the footprint that we want to use. So we are going to select that and create this temporary surface that we are going to use to make the comparison with newer SDB. So we call this surface LiDAR, 3-meter resolution, and This is from 2011. Okay, so we have now the first bathymetric surface that we are going to use for comparison. And now we look into the recent SDB data that we just received. So we filter our data sets to only the SDB data that we have right after the hurricane. So we don't have any survey in the area, and we need something to evaluate how the seabed changed after the hurricane. So we select this SDB data. So we can see here that it has a very high resolution, it's 2-meter resolution. So we are going to compare this LiDAR data set with this SDB data set that are very close in resolution. This is a fair comparison, and here it is. And we are going to do the same with this surface. We are going to create a temporary surface. So we create this temporary layer. And now we are also going to rename it as the SDB layer. From 2020. So now we have the two surfaces. And what we are going to do here is to use the raster calculator of spatial analyst tool. And we are going to create a difference image between this 2020 SDB data and the 2011 LiDAR data. Here's the raster calculator. Select the SDB data and make a difference between the two, between the SDB data and the LiDAR data. And the output raster will be a differential surface. And click Save and OK. Now the system is just comparing the two and making the differences. And we are going to obtain a delta surface. And here it is. This delta surface shows the difference between the two data sets. What we are going to do with this new delta surface is to also change the color ramp. So we can see here, and what we are going to select here is a color ramp that tells us where we have the largest differences in red and the smallest differences in blue. So we can see on the screen those differences pop up immediately to our visual inspection, and where bathymetry has more radically changed. And what we are going to do is to zoom into the bay to make a quick evaluation of changes that could represent a danger to navigation, a danger to ships that come as first responders with aid to the people, with aid to all those affected by the hurricane. So we can see here that there are some shoals near the coast on the bay, and this tells us very quickly that there is something that we need to pay attention to before we organize any activities, any supplies and medicines and help and aid coming from the sea. So now the next example that I want to show is for chart production. And what we are going to do here is to take SDB data And again, you can combine with all other types of sources for bathymetric data, from acoustic sensors to LiDAR to SDB, but we are going to use SDB data for this example for a rapid assessment on a chart. And we are going to create a triangulated irregular network surface, smooth that surface, extract contours, and import those new contours into an S57 database. We are going to show all this process step by step, but please keep in mind that all this can be automated. It can be stringed using geoprocessing and Python script tools. So please keep that in mind too, that if there are repetitive processes with the same criteria, you can automate those processes in one function. So here we are in ArcGIS Pro, and we have our area of interest. In this case is an ENC chart area coverage. And what we are going to do here is to convert our raster that we created with SDB data into make it a TIN, a triangulated irregular network raster. So we run the tool. And now in a few seconds, we will have a TIN. Here it is. So we have our TIN created, and what we are going to do now is to smooth this TIN. And we smooth the surface because we are going to create the contours, and we want those contours to be cartographically correct. Instead of having jagged lines, we're going to have more smoother lines. So we select our input data set is the recently created TIN, and we just name our output, our smooth TIN. And we select the number of iterations we want to apply to it to smooth the TIN. And this is something that you will learn with practice with the resolution of your data sets. It could be 15, and like in this case, it could be 10 iterations, it could be 20 iterations. The more iterations you apply to it, the smoother the surface you will get. So now that we have our smooth TIN, what we are going to do is to create the contours from that smooth TIN. Here's our area of interest, is the ENC area coverage that we are going to update. We select our input data set. We select, in this case, a contour interval of 1.8 meters. And the reason why we did it this way is because the ENC is coming from data that was originally in fathoms. So that's why you don't see like a round number. And you won't see round numbers also in the majority of the contour intervals. So here we have now our recently created contours. And what we are going to do here with these contours to finalize is to add the positive down to the value of the depth contour, because we had it in the BIS as positive up. So we change this to coincide with positive down in the chart. and we can check here the different contours that we are going to export. So as I said before, because this data is originally collected in fathoms, we have this these values in meters. So those contours that were selected are the contours that we want to use to update the ENC, and we are going to export those contours now to separate it from the total number of contours created. I'm going to give a name to that output data set. So once this is created, we just leave that data displayed. And this contour list is what we are going to bring into the nautical information system. Remember at the beginning of the presentation, I mentioned the ArcGIS Maritime solution. So what we are going to do here is to bring those contours into that maritime solution, the nautical information system, which can be considered as the equivalent to the bathymetric information system for bathymetry. So we are opening here the chart that we are going to update with those new contour lines, and we can see it here. And this is a geodatabase, but this geodatabase is based on the S57 data model. So what you see here is the equivalent of an S57 data set, but in a geodatabase using the nautical data model. So here are the contours that we are selecting. And it's going to be as simple as copying and pasting. So we copy those and we are going to put those into the depths, the line depths in the data model, and in the feature catalog subtype depth contour. So now we are pasting these new contours into the NIS. And now here they are. And we can check the attribute table of these data sets, and we can see them here. Now they're part of the NIS. And finally, I just want to, for sake of time, just want to show you the result. Here is the ENC with the new contours highlighted. So we have seen so far examples of analysis and production. In this case, we created an ENC. And again, this is going to be based on the uncertainty of the data that you use. If in the example, we use SDB data, but if the uncertainty is above the permissible parameters for certain types of scales, we won't use it. So the next example, and the last one, is going to be how to create a bathymetric elevation service with our bathymetric assets and using SDB for an initial evaluation of an area where we need to do a hydrographic survey. So this is an elevation service. This is in ArcGIS Server and using ArcGIS Online. And if we go here, we can select our data that we published from SDB and combined with other services. And in this case, we are combining it with the NOAA ENC service. So what you see underneath are the ENCs from the NOAA service. If we apply some transparency to the bathymetric data, we can see underneath the ENC bathymetry. And that gives us a very good tool for visual analysis. And if we go here, for example, in this shoal, we can see the shoal on the chart and the discrepancy in the position of the shoal that we see from SDB data. So that quickly gives us a clue of how the discrepancy is and where we need to pay our attention in planning the next hydrographic survey. If we query the data, we can see here that is almost 7.5 meters, and the shoal that's supposed to be 2 meters is 11.9 meters. So radical changes. You need to pay attention to this change and plan accordingly. So that's for planning in support of planning your hydrographic surveys. Another very useful way to apply SDB data. Another example could be, for example, combining other services like, for example, aerial photographs. So we bring this series of orthophotos that were taken right after the Hurricane Maria. We can see the different damages along the coast, and also evaluate where do you need to put your efforts for the first surveys and analysis of the changes in the coast and also in the seabed. Just an example, a quick example of how this can be used. We can zoom in, for example, here in this area, and we can see the damage in the shoreline, in the coastline, compare it with the shoreline in the ENC and with the bathymetry in both the SDB and the ENC, and make your priorities for new surveys. So these are the examples that I had today to show you the wide variety of applications of SDB datasets in a hydrospatial system. And I just want to give you with some conclusions. First of all, SDB data is very cost effective, is very quickly, and you can make assessments very rapidly about different situations without going to the field. SDB data is an excellent source for this type of assessments. SDB data can be used to complement chart data at small scales with all the caveats that I mentioned before. SDB data can be used for hydrographic survey planning, and as just shown in the last example. This data can also be combined with other bathymetric sources in a GIS, as we have seen in the BIS, how this can be combined with multi-beam, LiDAR, and single beam, etc. And a GIS platform is the best way to integrate SDB in a marine spatial data infrastructure to exploit and disseminate it to the largest extent to make it available to the a majority of people needing bathymetry. And this is what we call a hydrospatial system. So with that, I just want to give you here some resources that you can explore later, and you will have access to this information later, so that you don't need to quickly take notes of all these different links. But this is something that you will have available for you to explore some of the examples that we showed today. And with that, I just want to thank you all for your time. And we now have time for a few questions maybe, and hopefully we can answer them. If we cannot answer all of them, we will be addressing those individually to those that asked the questions. Thank you.
Steve, you're on mute.
Thank you, Kelly. We're a little bit over time, but we will take a couple quick questions. And Raphael, would you mind turning on your webcam as well? My name's Steve Snow. I work on Esri's national mapping team in Industry Solutions. I'll be the moderator here for this quick session. I'll try. I appreciate all of you staying on. I know this we've gone over time, but I'd like to go field a couple questions to our two presenters. And the first question I have is for Kyle. This one is focused on, you know, we can utilize satellite-derived bathymetry. Can this also work for unmanned aerial vehicles as well?
Oh, good question. Yes, absolutely. There's no reason this can't work for unmanned vehicles or manned aerial platforms either. The software we have in Esri we've processed aerial imagery to produce. It's not SDB, but it's aerial derived bathymetry and UAVs. So it's really about the camera and the multispectral sensor you have on your platform to produce bathymetry from it.
Okay, well, thank you, Kyle. The next question I have is from Vijay Kumar. And this one's for Raphael. Since littoral areas are dynamic, is it advisable to use old charts and ENC to train our data sets? I believe this is an AI question.
You're on mute.
Raphael, you're muted. Put $1 in the jar.
Yes, I think that jar is full already. Yes, you know, it is a valid approach. Yes, littoral is very dynamic and it changes due to erosion and accretion more rapidly in some places than others. That's why I think imagery is very important to make those initial evaluations. You can, of course, these days, and in the ArcGIS platform, you can start using artificial intelligence to detect those changes rapidly. But you could also do it visually. If you're in a very focused area, you could do that visually as an initial assessment. Depending on different factors, the coastal dynamics and the age of the ENCs and nautical charts, you may or may not use them as a comparison tool, but you can compare them against imagery. That's what I would do to make sure that there's a change that requires attention and update the chart.
Yeah, and for those users on here, earlier this year, we did a AI maritime webinar for detecting shipwrecks and shoal areas. So that recording is available online. Okay, so the next question I have is for both presenters. This is from Maria Hervé. What platform or software requirements are needed to use your software?
You want to go first?
Yeah, I'll go first. So our satellite bathymetry multispectral software tool works within the ArcPro as software. You do need ArcPro. That does not work in ArcMap. You do need image analysts to use some of the tools, as well as 3D analysts. But basically, the general tools will work with the basic standard ArcPro license. And there might be some bells and whistles that won't work if you don't have 3D analysts or some of those, but in general, it'll tell you if it's not going to work, and it'll use the tools that it's allowed to use. So you don't need to have those extensions, but those do provide enhanced features within the software.
Right. And in our case, yeah, it's ArcGIS Pro to do all the analysis that you want to do with the data. If you want to have the specific applications for the bathymetric information system, today we have it in ArcMap. So it's the ArcGIS desktop tool of today. And this is being ported into the ArcGIS Pro platform. And the tools will be available in the Pro platform by the fourth quarter of next year. But today you need ArcMap. If you notice in my examples, I used a combination of ArcGIS Desktop in ArcMap and ArcGIS Pro. So we are in this process of transitioning between the two platforms, but don't worry, we try to make that as smooth as possible, and working with the BIS in ArcMap enables you to also use ArcPro for certain tools. So you don't need to buy tools, the two platforms separately. They come together. And if you already have an ArcGIS license, you already have Pro available.
Okay, well, thank you, Raphael. Okay, so I'm going to move on. We've got another hopefully quick question. It says, thank you. This is from Dennis Haynes. Thank you, Mr. Ponce, for your presentation. In your hydrospatial example related to the hurricane in St. Thomas, did SDB allow to pinpoint specific hazards such as shipwrecks?
Well, you could pick different things. Shipwrecks could be seen as shoals in the results. Perhaps Kyle also can talk about that. But in our example, what we showed in our example was variations in depth. And of course, if you have a conspicuous shape in that shoal, that could be an indication of a wreck. I don't know how much definition you would have from SDB data, but definitely you will find the discrepancies and then do further investigation.
Okay.
I would just add that that St. Thomas area, the image was taken long after that hurricane. It was very far after, so there weren't really any wrecks to be found in that case. But yes, you could identify small wrecks. You know, you aren't limited to the pixel size to find small wrecks, but you do see that as an obstacle or an object in this SDB that then you'd go and interrogate with a satellite image and identify see it as, oh, that's not just an obstacle, that's an obstacle and it's a wreck.
Right. Yeah. The SDB data was from 2020, and the hurricane hit in 2017. Yeah, 3 years ago.
Okay. So moving on quickly, this one's from Kevin Critchlow. Is there any access to the SDB toolbox for teaching?
Oh, good question. I've not heard that one before. I'd love to take that offline. Yeah, we could probably do something for that.
Kevin, we'll try to follow up with you on that one.
We do work with a number of academic professors and such who have tested and trialed our software, so it's definitely useful for us. So we welcome that collaboration.
I could see them needing this. Okay, so quickly, this is from Christina Belton. Will you provide written steps to achieve the results you showed in these demos? I guess this is for maybe Raphael or Kyle's, whichever.
Well, yeah, in our case, there are no written, but one thing that we want to do is to make these tools, these configuration tools, available later in our resource center. I think we are going to put them, we have an Esri Hydrographic Office ArcGIS online account where there is a place for resources. So probably we are going to put those tools there available, as well as GeoNet and maybe GitHub.
Maybe since Esri will be participating in 2021 at the US Hydro Conference in September, maybe this is something, if you'd like to attend, maybe Esri could put something together.
Mm-hmm.
Yeah, I would just add from TCARTA's side that we do make our written kind of instructions available for software users, as well as tool tips and all that. We also provide training along with the data sets to train people to educate them how to use it. We definitely see satellite derived bathymetry as a bit of like a digital trade craft, and it's something I can give you tools, but you need to actually know how to use them and understand them. So we do offer that as well to complement it, because you give the keys to a car that goes 0 to 60 in 2 seconds, you're going to crash it in no time. So we want to do this in a smart way, so you're producing good data and managing it properly. So we're here to support that.
Okay, another really good one, and this one's from Lindsay Haynes. Excuse me if I said the last name wrong. How much does the ability of SDB vary with water clarity? The water in St. Thomas is very clear, but what about murkier water, say off the coast of I believe California or Canada? So.
Okay. Yeah, absolutely. Water clarity does matter significantly. St. Thomas and Caribbean is a great test bed. We can mitigate lots of fair bit of water turbidity. We largely do that with repeated imaging the area and get seasonal variations to find clear waters. With offshore winds can often bring clear water towards coastal areas, or synchronizing it with the tides when we're able to dictate when the image is collected using a worldview satellite. We can task an image when the clear water is coming in with the incoming tide, for example. That said, there are some areas that it's never going to work. Very turbid areas can need water going through the water column and back up to the sensor. So there's a lot of tricks and tricks we can do to mitigate it, but it's not an absolute. It's not going to work in every situation.
Okay. Well, I'm going to take this one last question. We are way over time. I'm sorry, gentlemen. So this one's from Craig Green. The question is, the bathymetric smoothing tool uses a shallow bias algorithm so that the generated contours will have is that a question or more of an answer?
I think it's a comment. I think it's a comment, but it's a very valid comment because I didn't mention that in my presentation. Yes, this extraction of contours are shoal biased. You can configure that when you extract soundings and when you create contours. It could be deep biased, shoal biased, average biased, but in this case, for this example, because we were populating a navigational product, it was shoal biased.
Okay, perfect. Well, Kelly, would you mind closing this out and comment a little bit about the presentations and the recording? We've got a ton of questions on when those are available. Would you mind answering that and then close it out for us?
Yeah, no problem. Thank you, Steve. So to answer everybody's questions, the webinar in its entirety has been recorded, and we will be providing a public link to this recording to everyone via email. So that should send out within the next couple of days to the emails that you've registered with. And with that, you should be able to share that link to any of your colleagues. We welcome the additional views and collaboration on our webinar. With the post on the public link, you will also find additional resource links that we have provided for you. So make sure to keep an eye on your email over the next 2 days. And again, I'd like to thank everyone for attending our webinar. A big thank you to all of our presenters today and Steve for moderating our Q&A session. And again, keep an eye on those emails. We will be addressing any questions we missed within that post as well. So don't worry if you had a question that went unanswered. We should be able to get to you within a couple of days. So again, thank you very much for your participation. We appreciate everyone staying on for the additional time. And with that, I will close it out and wish everyone a great rest of their day. Thank you.